Okay, let's dive right into this. Welcome, Focus Lanners, to today's Explainer. I am absolutely thrilled to have you here because we are looking at a topic that will literally change how you see the world around you. We're going to explore the illusion of pigment and unpack the hidden physics of light. Because as you'll see, a lot of what we perceive as color doesn't actually come from dyes or paints at all. It comes from the actual physical architecture of light itself.
Now, you might be wondering what's going on here. The sheer mystery of this is fascinating. I mean, it's just a common oil slick in a puddle on the asphalt. There are absolutely no chemical dyes or pigments mixed into that oil to produce those vibrant, swirling greens, purples, and blues. It's completely colorless oil floating on clear water. So how on earth do we see a rainbow where there is inherently no color?
Well, the secret behind those beautiful colors is a phenomenon known in physics as interference. In the simplest terms, interference is the redistribution of intensity that happens when superposed light waves interact. Or, to put it even more directly, it's what happens when light waves literally crash into each other. Depending on exactly how they crash, they fundamentally alter what our eyes detect. Think of it like throwing a couple of stones into a perfectly calm pond. When the ripples meet, they interact, right? Where two crests of a wave meet, they build each other up into a much larger wave. That's a high-intensity region, or constructive interference. But where a crest meets a trough, they cancel each other out entirely, leaving the water totally flat. That's a low-intensity region, or destructive interference. Notice the black and white wave pattern here? Light behaves the exact same way. The bright bands are where light waves build each other up, and the dark bands are where they cancel each other out into total darkness.
Let's move to the mechanics of light interference and see how this builds. Because, as it turns out, light doesn't just do this randomly. There are strict rules governing how and when we can actually see these incredible patterns. For engineers to manipulate light, they have to control three foundational factors. First, the light must have coherence, which is an absolute necessity to create a pattern that stands still long enough for us to see it. Second, it's best to use monochromatic light, meaning light of a single wavelength or color. If you mix too many colors, it just creates messy patterns that blur together. And third, the interfering waves should ideally have equal amplitudes. It's not strictly necessary, but it gives us that stark visual contrast between the bright and dark bands. I want to pause on that first rule for a second, coherence, because it is vital. You absolutely cannot get a stable interference pattern just by shining two random flashlights at the same wall. Light from two completely different sources is chaotic. The waves are totally out of step. For a visible pattern to emerge, the light waves must be perfectly synchronized. They need to act like a perfectly coordinated marching band. This is what we mean by coherent sources. And usually, the best way to get this is to take a single light source and physically split it so you know the resulting waves are perfectly matched. Okay, moving on to the math of visibility contrast. So how do physicists actually measure this? Because in advanced engineering, looks pretty sharp just doesn't cut it. This brings us to the visibility formula, which is a brilliant piece of math used to calculate visual contrast. Visibility, or V, is basically the maximum intensity minus the minimum intensity divided by the two added together. So V equals Imax minus Imen over Imax plus Imen. This simple ratio dictates exactly how crisp and sharp the light pattern will appear to our eyes or to a camera sensor. So the crucial point is how this plays out in a real measurement. Let's look at a concrete example of the formula in action. In a scenario with perfect contrast, let's say your bright band has a maximum intensity of 100 and your dark band completely cancels out, leaving an minimum intensity of 0. If we plug that in, 100 minus 0 is 100, divided by 100 plus 0, which is also 100. That gives us 1.0, or 100% visibility. You get incredibly sharp, crisp bands. But what if the destructive interference is weak? Say Imax is 100, but Imin is 80. Well, 100 minus 80 is 20. Divide that by 100 plus 80, which is 180. 20 divided by 180 gives you about 0.11, or roughly 11% visibility. The visual result? A blurry, washed-out mess. Let's transition over to wedge films and measurements. This is where we go from abstract formulas to physical, real-world applications. Imagine you need to measure the exact thickness of a single human hair, but you don't have a microscopic ruler handy. What do? You simply place that hair between two exceptionally flat glass plates. Because the hair props open one end, it forms a microscopic wedge of air between the plates. When you shine monochromatic light straight down onto this, the light reflecting off the top plate interferes with the light reflecting off the bottom plate. By simply counting the resulting bright and dark stripes, the fringes, you can calculate the exact diameter of that hair. It's a real game changer. And this fringe counting technique isn't just a neat lab trick, it is entirely vital for modern manufacturing. Industry relies heavily on wedge interference to test surface flatness for microscopic defects. If the fringes are perfectly straight and parallel, the surface is flat. If the fringes warp even slightly, you've got a defect. This exact same principle is used to check the quality of camera lenses, telescope mirrors, and glass prisms. It allows engineers to achieve precision measurements with literal sub-nanometer resolution.
Which brings us to thin films and advanced tech. Let's broaden the scope of this explainer a bit, because beyond just measuring things, manipulating layers of light actually powers multi-billion-dollar tech industries through what we call thin film technology. Think about the glasses you might be wearing right now, or the camera sensor in your smartphone, or even solar panels on a roof. They all use single or multi-layer dielectric films, anti-reflection coatings. By deliberately engineering a thin film to cause destructive interference for specific wavelengths of light, we can effectively cancel out the reflection. Instead of light bouncing off and being wasted, it transmits straight through. This is what vastly increases the efficiency of a solar panel and perfects the contrast of your camera lens.
But how thick should these magical coatings actually be? Well, the foundational design parameter for an anti-reflection film is a rule beautifully summed up by this simple expression: lambda/4. We call it the quarter wave thickness rule.
To really ground this formula, let's look at an example. Let's say you're engineering a solar panel, and you specifically want to stop it from reflecting green light, which has a wavelength, or a lambda, of roughly 500 nanometers. You simply take that target wavelength and divide it by 4. 500 divided by 4 gives you exactly 125 nanometers. If you manufacture your coating to be exactly 125 nanometers thick, the light waves bouncing off the top of the coating and the bottom of the coating will be perfectly out of phase. They cancel each other out entirely. The reflection disappears and the panel absorbs the energy instead.
And this brilliantly illustrates exactly what we're talking about in the real world. Here we have two highly specialized examples: the nose of a massive Airbus commercial jet and a precision piece of optical glass. Take a look at that strange, colorful rainbow effect on the cockpit windows of the Airbus. Now, a multi-million-dollar jet doesn't just have oil slicks left on the windshield, right? That is an intentional thin film interference effect. The window is actually coated in indium tin oxide, or ITO, which acts as a defrosting heating element. Engineers intentionally make the thickness of this film non-uniform, meaning it varies slightly across the glass, so that the window heats evenly at different distances from the electrical connections. And that varying thickness creates varying interference, giving us that rainbow pattern.
Now, on the flip side, look at that perfectly flat optical window. It has an anti-reflection coating precisely engineered to work when you look straight at it, at a 0-degree angle. But watch what happens when you tilt it to 45 degrees. The angle at which light travels through the film changes the physical path length of the light wave. So to the light, the coating suddenly seems thicker. Because the apparent thickness changes, the interference changes, and the center wavelength shifts toward red. This means the window suddenly starts reflecting vibrant violet and pink light instead of being totally transparent. But you know, as incredibly advanced as our technology is, it is vital to remember that nature completely beat us to the punch. It mastered this physics long before human engineers even existed. The spectacular iridescent colors of a butterfly's wing, or the brilliant blues and greens of a peacock feather, those aren't made of chemical pigments that fade in the sun. They are what we call structural colors. They rely entirely on microscopic, highly ordered biological structures to create wavelength-dependent constructive interference. The color is literally built into the physical architecture of the feather itself.
So what does this all mean for us? Well, here is the ultimate question to wrap up today's explainer. We've seen how thin films and interference can perfectly manipulate light to create any color imaginable without a single drop of dye. As we get better at nanofabrication, could engineered structural colors, ones that never fade and never degrade, completely replace the toxic, environmentally damaging chemical dyes we use in our clothing, our paints, and our everyday world? It's a pretty mind-blowing thought, isn't it? The untapped potential of physics to radically reshape our future is quite literally right in front of our eyes. Think about that the next time you see a puddle on the street. Thanks for joining me on this explainer, Focused Learners. Keep asking questions, and I'll catch you next time.